My work was challenging. It was very interesting. I felt a lot of times like I was playing.
It gives you the opportunity to make the connection between what you're learning in class and what you're going to learn in the real world in a job course.
It allows you to see what you're doing and see how it's being implemented and actually see the change that you're working to create.
I don't really get to do too much collaboration in school. It's mainly just individual projects, so also working with others has been super important. I've never really done that before.
It was the first place that I felt like I belonged, and the first place that I felt that my crazy ideas weren't so crazy.
This experience for me has really been phenomenal. I've made some great friends, had a fantastic summer, great networking opportunities, and the projects you get to work on are like nowhere else.
Welcome everyone to this year's Engineering Career Day event. My name is Carol McKisson. I work in the Science Education Department at Jefferson Lab, and I'll be your host. Today's event is a collaboration between Jefferson Lab, NASA Langley Research Center, and Newport News Shipbuilding. To kick off today's event, you'll hear from our keynote speaker, Dr. Renuka Rajput-Ghoshal, followed by a Fun with Physics demonstration by ODU Professor Dr. Larry Weinstein. After that, we have the engineers panel, where you'll hear from a panel of engineers representing each host organization. Lastly, you'll hear from the Peninsula Engineers Council Doug Ensor Award winner, Dr. Robin Hunt. We'd like to thank the Peninsula Engineers Council for once again sponsoring this event each year. We also have an exciting Team Cyber Challenge this afternoon, provided by Lawrence Livermore National Laboratory. For those of you who have registered to participate in this Cyber Challenge, it will be held this afternoon from 12:30 to 2 o'clock Eastern Time. If you are interested in participating in the Cyber Challenge and haven't registered yet, it's not too late. Registration closes at 11:30 Eastern Time. During the engineers panel discussion, if you have any questions for the engineers, please submit your questions in the chat, and they'll be answered in the chat. And now I'd like to introduce our keynote speaker for Engineering Career Day 2022, Dr. Renuka Rajput-Ghoshal. Renuka has been working with the Magnet Group as a senior superconducting magnet engineer at Jefferson Lab since 2013. Renuka earned her Bachelor of Science and Master of Science degrees in physics from the Rohilkhand University in Bareilly, India, and a PhD degree in physics from the Jawaharlal Nehru University in New Delhi, India. Thank you so much for joining us today, Renuka. We are so excited to have you as our keynote speaker and for today's event and for you to tell us your story.
Thank you, Carol. So good morning all. First of all, I would like to thank the organizer of the event and Jefferson Lab Education Department for giving me this opportunity to talk to you all. I wish this was in person where I could see you all and interact face to face. I like working with the students, whether it is a STEM career day or getting involved with the student during their visit to lab. And today I will like to talk to you about myself and what I do at Jefferson Lab and what brought me here. So for that, I have a very small slideshow to share with you all. So about me. So I was born in a small village in North India, which is like showing with the red pin here. And I will just tell a little bit about my village and my journey here. So this is a very small village. Population is about 1,300, 50-50 male and female ratio. But when I was born, there was no electricity in the village. And There was no shop, no library, no hospital, no public bus or transport there. So nearest public bus and all those things were almost 10 miles away from my home. But good thing was there was one elementary school in the village. But this school was very small with one room, one classroom and one small office room. And literally the roof of the schoolroom was almost missing. So it was just kind of open ground. So in summer, we will sit under the trees, and in winter, we will sit in the sun and do our education. Again, like as you can assume, the quality of education was really poor. So after my elementary school, I moved out to a city where I did my other education. Other problem during my childhood was the girl education was not given much preference in India. But I was fortunate to be born in a family where girl education was very, very important. So my father was a very big supporter of girl education. And my mother, she was very good in math, mainly like numbers. And she will just make sure that we all siblings know our numbers very well. And we do our mental math every day before going to bed. And my father, he was the one who inspired me to be curious and ask questions. So my village, like if you just see here, it is very close to these mountains, which is like Himalayas here. So my village is in the valley. So this is really a beautiful place. You can see the Himalayan mountain from my rooftop. And this village is surrounded by a lot of river around there. And I remember very well when I was a little child, my father will take me to the my father will take me for a walk to the river, and I will have a lot of questions to him. And he will always listen carefully and he will try to answer me. So my questions used to be like, why this river flow in this direction only? Why doesn't it change direction? Why these mountains are so high? Why these mountains don't move? Can they come closer to our home? So all those kind of questions were there, and he will really, really listen very carefully, nicely, and try to give me some answers. And as I told, there was no library. So whenever my father used to go to the nearby city, he will bring some science magazine and some storybooks for me. And I loved to read, and I tried so many small experiments using this science magazine at our home. So that's how my childhood was. Now I will just tell a little bit. So I started college when I was just 15, and I finished my PhD when I was at the age of 24. And this is how my journey is. So from India, I went to UK, and then from UK, I went to New York here, and then now I am in Virginia. I did all my education in India, as Carol mentioned. And during my education time, I was very active in debating society and other academic group. I was not at all in sports. Then there I designed India's first NMR magnet. NMR stands for nuclear magnetic resonance imaging. And then I worked in Department of Atomic Energy of India for about 6 years. Then I moved to England. I got married there. We had our daughter there. And there I worked for 2 different companies, again, like making superconducting magnets. And I worked there for almost 9 years. And this shows one of the magnet, and I will talk about that in my later slide. Then in 2011, we moved to New York. And there I worked in GE Research Center for 2 years, where I was working mainly on MRI magnet and superconducting wind generators. And then from 2013 to now, I am working in Jefferson Lab, which is almost 9 years. And here I design different kind of superconducting magnets and other types of magnets for physics research. So these are some of the magnets I worked. So this is a picture taken from the book on superconducting basics and magnets. And if you just see, this is me here. And this was, I think, in 1993 or 94, something around that time. This is one of the magnet I worked for Oxford Instrument. This is like 400 megahertz NMR magnet, which is almost like more than 9 Tesla field. This is one of the magnet which you show in the last slide. So this magnet is AMS, which is alpha magnet spectrometer. This magnet was supposed to be going to a space station. So we made it for that, and finally for some technical reasons it couldn't go there. Then this is another magnet which I worked on when I was in England, but this magnet is being used at Oak Ridge National Lab, which is another national lab here in US. And I'm showing this magnet because this is a very complicated magnet to design and to build. These 2 magnets are for Hall B in Jefferson Lab. So this is a big torus magnet. And if you just see, this is like more than an 8-meter size magnet. Other magnet is this 5 Tesla solenoid magnet. Again, this is important because this is I think this is the highest magnetic field magnet in Jefferson Lab and highest stored energy magnet in Jefferson Lab. Now, what I am doing now, so currently I am working on this project, which is electron ion collider, and this shows the, so this project will be at Brookhaven National Lab, and Jefferson Lab is the major partner in this project. So this project will be using the existing facility at Brookhaven National Lab, where they have some of those rings and some of them they will make new. So this machine, it will be a discovery machine, and this will be used for unlocking the secrets of the glue that binds the building blocks of visible matter in the universe. And in this machine here, the possible detector location here in this location will go this detector, and this purple thing here, this is the magnet, and this is what I am working on right now. I live with my family, so it's my daughter who is a junior, my husband, and my 1-year-old doggy here, and we enjoy going on walk and doing other things. Now at the end, I just always like to give some suggestions to all the students, and these are my top 10 suggestions for all of you today. First is be honest. So honesty is the best policy, we all know. But if you just think in detail, if you are honest, you can learn a lot from your teachers. If you tell honestly your teacher that you don't get this, whatever the teacher is trying to explain, at least they can try again. But if you are not honest, teacher will not know, and you will not learn anything. Second thing is respect your teachers. So if you just think about that, if there are no teachers, there won't be any scientist, doctor, or anybody. So you should respect your teachers. And your teachers will be very proud of you for all your success in your life. And respect them for their hard work and time they devote for you. The next one is trust your parents. So parents are the only people in this whole universe who wants you to see happy. And your happiness is their success in life. That's what they want only thing from you. If you have any doubt in life, talk to your parents. They know and understand you better than anybody else, even better than you. The next one is value your friendship. A true friend is the only person who will be with you in each and every moment. And that person will stop you doing any wrong things in your life and encourage you in your low moments. So having a good friend is really very important in your life. Then respect everyone, whether a person is older than you, younger than you, richer than you, poorer than you. So just see like how nice, how much better this place would be if we all respect each other. The next one is be inquisitive. So question yourself and question others. Just think like how these things work. If you just devote your time in thinking and learning how things work, you will learn a lot. Use your local library and internet for learning all these things. The next is dream big and work hard for achieving those dreams. At least some of those dreams will come true. I know like we all dream, but not all of our dreams will come true, but at least some of them if we work hard. Help others. Help everyone around in your best capacity. And the next one is don't compare yourself with others. So if you want to just be like your friend or be like me or be someone, don't do that because we all are different from each other. Just be yourself and work hard for that. Then at last, encourage each other to be a good human being. And this is all kind of my suggestions for all of you. I hope you can use all these and maybe one day you will be successful in your life and you will be doing something great in either science or some other academic field. So that's all I have to say. Thank you so much for listening to me, and I will stop sharing.
Oh, thank you, Renuka. I love your 10 suggestions. What great suggestions for everybody to get through life.
Yeah, that is true for everybody. Yeah.
Well,
thank you so much, Carol.
I appreciate you joining us today and sharing your story with us. And what a story. If we have any questions about magnets, we know where to go. Okay, thank you so much, Renuka.
Yeah, thank you, Carol. It was really my pleasure to be here with you all today.
Up next, you're in for a treat with Dr. Larry Weinstein from Old Dominion University with his Fun with Physics demonstration.
Welcome to the Physics Fun Demo Show, everyone. My name is Larry Weinstein in the Physics Department at Old Dominion University. This is my lovely assistant, Perry Nero, and we'll be demonstrating some of the wonders of physics for you over the next few minutes. So what I want to start with is the seat of nails. This seat has several hundred sharp nails on it, and well, you know, people will tell you that you need to be getting that really spiritual frame of mind in order to sit on a seat of nails. But it's actually really just physics. You just sit down, there you are, and you're just fine. Now, what I like to say when I invite people up to try the seat of nails is I ask them, have you sat on a seat of nails before? Most people will say no. And I'll say, try the starter seat. It only has one nail. That gets the point across. Because with 300 nails, it spreads the force out over all 300, and I can sit on it just fine. Speaking of pressure, the next thing that I want to look at is water pressure. So what I have here is a pan balance, and it's balanced. I've got mostly balanced. There's a beaker of water on one side, there's weights on the other, and you know, if I put a little force down here, that goes down. If I put a little force here, that goes down. The question is, and think about it before I do it, if I put my finger in the water without touching the sides or the bottom, what's going to happen? This side can rise up, it can stay the same, or it can go down. Think for a couple seconds. Here we go. So I put my finger in the water without touching the sides, and it made this side heavier. How'd that happen? Well, my finger's pushing down in the water, my water's pushing up on my finger, so my finger's pushing down on the water, so it's adding force to this side, and it gets heavier. So the question is, what happens if I put a piece of cardboard over this cup and turn it upside down? So here we go, piece of cardboard on cup, oh, it doesn't stay. But if I fill the cup with water, and then I flip it over, then, oh, wait a minute, the cardboard's staying. How'd that happen? Well, right now there's lots of water inside, but there's air pressure, and air pushes really hard. There's a vacuum up top, so we've got some water pushing down, all the air here pushing up. If I can let air into the inside, then it lets go. So on the nature of how hard does air push, we want to take a look at how hard air pushes. So here we have an empty sphere, nothing inside. Well, that's not quite true. There's air inside. And so if we can in fact replace the air with nothing, with a vacuum pump, and that's what we're doing now, is we're sucking the air out, turning on the vacuum pump. Here we go. Pulling out the air. Now I'm going to close this valve, and we'll turn off the pump, disconnect it, and now it doesn't come apart. And in fact, we can pull really hard, and it's not going to come apart until, watch out now, I open the valve, let air back in. So if I've got air inside pushing out and air outside pushing in, it's really easy to pull apart. If there's air outside pushing in, nothing inside pushing out, then we can't pull it apart. So let's take a look at this with a soda can, because that thing's made of steel. It's pretty strong. We're going to do it with a soda can, which is not very strong. So let's see what happens. So the first thing I need to do is to light my propane torch. Now I'm going to take just a standard empty soda can and put in a little bit of water. Not too much. Not even an ounce. I'm going to take a sophisticated vacuum valve. This is called a piece of cardboard. Put it over the top, just to block the path of it. Then I'm going to heat it up. I'm going to put it in the propane, and the propane is going to make the water boil. When water boils, it takes 1,000 times more volume, and now I've got air on the outside pushing in, I've got air on the inside pushing out. I've got air on the outside pushing in, I've got water vapor on the inside pushing out. You can see it's boiling furiously. If I can get rid of that water vapor, then the can crushes. Because once I dunk this can in the water, all the water vapor that was inside condensed. I had air on the outside pushing in, nothing on the inside pushing out, and the can went crunch.
All right, so continuing with this idea of what can we do when we heat things up, I've got two balloons here. One's just filled with air, and one's got a little bit of water in it. So you can hear that. All right. What I'm going to do is heat them up. Take my candle. All right. Bring my balloon in nice and close, and see what happens as the rubber in the balloon starts to heat up. Suddenly it pops. All right. So let's try that again. Let's use the water balloon. So this time, all right, same type of material, but it's got a little bit of water in there. Bring it towards that flame. What's going to happen here? Am I going to make a big splash? Nothing's happening. Why is that? Yes, with the previous balloon, the candle was able to heat up the plastic, melt it a little bit, cause it to pop. But here, there's that water that's inside the balloon. And so we're heating up the water as well, preventing the rubber from reaching that critical limit where it suddenly fails and pops. So we've got a camera aimed at me so that you can see how I'm glowing in the infrared spectrum. You can see different objects on me, like I've got a pocket protector here. Nice and cold. Go to my exposed skin, nice and warm. So let's see what kind of thermal objects we can play with here. I take myself in view, got myself some cups of ice. Let's aim at that thing, right? So I've got cups of ice. You see how they're that nice dark color in the camera? It's because of how cold this is. The temperature setting is scaling these away. Now if I switch to something like nice thermostat, warm water, you can see down here in the cooler region, right? This thermostat is trying to keep the hot water that's inside the cup contained. But you notice up here, see how it's a little bit warmer? Because that water is escaping, right? Should be good to pour. There we go. All right. As I pour that hot water, you can see that wonderful temperature changing, moving around the cup. Throw some ice in there, start melting it. What are the other things we can do with this camera? We can talk about how visible an object is to the infrared spectrum. Because the camera that you're seeing me at right now is looking at the visible spectrum. And I've got a black bag here. If I was to stand in front of the bag, you wouldn't see my face. When I look at the infrared camera, take that black bag, and you still see my face. Try and wiggle my eyebrows if you can see that. Right. So even though on camera, in the visible spectrum, this bag looks opaque. It looks like you can't see it. To the infrared, the rays go right through. What about this? Got myself a nice piece of glass. On that camera, you can see me nice and easy. Bring it over here. And I've blocked myself out. Take out my heart, right? Go back to my face, right? So here's material. Here's an example of something where in the visible spectrum, right, the light's able to transmit through, yet something in the infrared, the temperature we tend to associate with warm, hot objects, it's completely opaque, completely blocks out. Try writing messages on this. we've all heard this idea that warm air rises. And so what we have here is a strange type of beaker. It's filled with liquid. I'm just going to put a little green dye in there. Give it some color. All right. So you can see that the liquid is pretty stationary. What I'm going to do now is introduce some convection. I'm going to heat up this corner here. We'll try and just get this corner here nice and warm. And we'll start to see how, as the water gets hotter here, let's get that a little bit closer. We're going to start to create a flow. You can see how the currents are being generated here. That warm air, in this case the warm liquid, is being pushed up into a less dense region of the tube. As it rises, it tends to cool off, come back here, start to fall. And now we've created this convection, right? We've created this cycle of the warm material rising up and flowing things around in this circle. All right. We've almost completed our first loop. And we can keep this going on. Take the heat away. You can start to see where the warmest regions is as it's trying to convect around, flow. Let's get me out of the way.
Okay, so the next thing that we want to look at, Perry, if you would take this away, please, is we want to look, since we started looking at moving fluids, we want to look at what happens when the fluid, which can be a liquid or a gas, moves quickly. So for this, I'm going to take off my mask. And the question is, what happens when air moves quickly? Well, there's an easy demo I can do. I can just blow over the top of a piece of paper. And if I do that, you think, well, gee, the air's rushing out, it's going to push the paper down. It doesn't. The paper rises up when I blow on the top side. And that's because a moving fluid actually has less sideways pressure than a non-moving fluid. And this is part of the reason why airplanes fly. It's a bit more complicated, but this Bernoulli effect is part of that. And we can see that with something else, where I'm going to take this blower to give me a current of air. This blower is blowing air straight up, and I can suspend this ball in the current of air. Now, that's not terribly surprising, because the air is pushing up, gravity is pulling down, but I can also tilt it a bit, and it's staying in the airflow. That is weird. Now, if I tilt it too far, it falls out, but it's staying in that airflow, and it's stable, because the air going up, it's fastest in the middle of the flow, there's the least pressure, and the ball stays where the pressure is the least. I can demonstrate this another way. I have here a complicated scientific device where when I blow into it, I make a current of air going up, and the eyeballs stay suspended. The last way I can do this is I have a funnel and a ping pong ball. And if I put the ping pong ball in the funnel, it's not going to stay there. But if I can blow through the funnel, wait a minute, you're thinking he's blowing down and it's going to make the ball stay up? How does that work? Well, like this. As long as I'm blowing, that ping pong ball is staying up, and the reason for that is that the fast-moving air has a lot less sideways pressure than the regular air. There's less pressure up here where the air is moving really fast, more pressure from below, the ping pong ball stays up. That's called the Bernoulli effect. We can see another couple examples of what that does. So, take it away, Perry.
I've got here what we call an air cannon, right? Just a little spring-like area. I'm going to spray some smoke in here, or just a can of smoke, and start seeing what happens when we have some flowing air. So let's fill that up for a bit right now. Just get a nice, decent amount of smoke up into this thing. Keep going for a little bit longer. Let's start there. We'll try and go across the camera. Get ourselves these wonderful smoke rings. Do one shot at the camera. And you can see that you get this actual ring shape of the moving smoke cloud due to the cut off of the shape here. So, another one we can do. Start applying Bernoulli's principle. All right. We talked about how I can reduce the pressure in a region. So what I'm going to do is use my can of air, my air cannon, to knock these things down. So let's get my aim right. I'm aiming right between the two. What happens when I hit? They moved in. We'll set that up one more time, put a little bit more space between them. All right. So I'm not aiming at a cannon. I'm not trying to knock one down. I'm going in between and seeing what happens to those soda balls when that rush of air flies by, reducing the local pressure. That flowing air, when that air is in motion, the pressure around it is reduced. So some other things we can do with this. All right, we're trying to exploit the objects moving in air. Right? Has anyone ever thrown a curveball? What's the trick? You take your baseball and you gotta give it a good spin. Well, I'm gonna cheat. I have myself here, a nice little thrower here, got some sandpaper in it. That allows me to grip this really well and give this ball a nice, great spin. Let's get this camera out of my way. What I'm gonna do is try to give it a spin. I'm gonna throw it straight like that. Watch the curve of the ball. So notice the curvature of the ball. That rotation is changing the air pressure around it. So we'll try to throw at the camera, and I'm going to curve it sideways. So again, so I'm throwing at the camera, and we see the curve. One more. And we see the curve caused by that rotating object to cause it to arc in the air.
Okay, so we've been looking at heat, we've been looking at moving air. Let's go back to heat and take a look and see what materials do. We already said when we heat water, it expands, it becomes less dense, it rises. And we saw that with the convection. Here what I've got is I've got a plate, I've got a ball. The ball does not fit through the plate. So the question is, what happens when I heat up the plate? When I heat up that aluminum plate, aluminum is going to expand. So here's my aluminum plate. I'm heating it up. When the aluminum expands, is the hole inside going to get bigger or smaller? So I'm heating this up, and am I going to be able to get the ball through the hole in the plate once I've heated this up? So it'll take me a few more seconds to heat it up. I've got a lot of aluminum here. It's a fairly thin plate, but it's fairly large. And so we've heated up the aluminum plate. And when the plate gets bigger, the hole gets bigger too. Huh, interesting. So what happens is that when the aluminum plate expands, it's kind of like blowing it up on a Xerox machine. The outside gets bigger. Yeah, I touched it, I'm an idiot. The outside gets bigger, it's hot. The inside also gets bigger, the whole thing gets bigger proportionately. Now, the other thing we've looked at before is we've looked at air pressure. And what we've said is that, great, thank you, air pushes really hard. And so what I've got here is a thing called a vacuum cannon. Here's my projectile. It's a ping pong ball. I'm going to drop it down. There's nothing inside this. This is just an empty PVC pipe. I've got an inlet here so I can use a vacuum pump and suck the air out. I've got a piece of aluminum foil on the end. That's my vacuum seal. Not very strong, you're thinking. You're right. And here, on this end, I've got the top of a soda can, and I'm placing it on. And now, this is reasonably airtight. So I'm going to take the vacuum pump, plug this in, and before you turn it on, we're going to pump it down, and then the aluminum foil is going to rupture. That ping pong ball is going to come flying out. You'll hear that impact. Go ahead and turn it on. So here we go. And the ping pong ball shot out, hit the wall, bounced over there. The first time I did this, I did it in a middle school auditorium with a racquetball. The racquetball hit the far end of the auditorium with such an audible thwack. I was grateful I hadn't hit any of the students. That could have been interesting. So, we've now looked at what happens with pressure, that air pushes really hard. We've looked at temperature, that heat makes things expand. We've looked at water, that water can absorb a whole lot of heat. The next thing we're going to do is we're going to look at extremes of cold. So now what we're going to do is we're going to look at the properties of liquid nitrogen. And nitrogen's in the air all around us, but the question is, what happens when we make it a liquid? Take it away, Perry.
All right. As usual for safety, I'm going to use gloves because we're dealing with some pretty chilly stuff. All right. Take my little doer here. I'm just going to pour it out right now. Pour it into this display doer here. Oh. Watch it fill up. Oop. You're seeing a mixture of the liquid going into the doer and all this fog around it. Now fog is mostly water molecules in the air condensing down. Probably a good amount. Put that on the side. All right. So let's take a little ladle, scoop some of that stuff out, try and convince you it's a liquid. And we'll just dump it on the floor, on the tabletop here. You see it instantly evaporating. This stuff is so cold. It's so cold that in our room temperature, it's basically boiling. So we got this constant boiling material as we're flowing around. So let's get some into a nice clear cup. Probably easier just pour it in. Come on. There we go. So you can see how it's constantly, it looks like it's water that's boiling, but that's this liquid nitrogen just constantly evaporating in this area around us. Nice clear substance. You can see as I put it down, it touches that warm table, starts boiling over and over.
So Perry's been referring to this as really cold, but the question is it cold or hot? I've got a tea kettle. Now, when tea kettles whistle, it's because they're really hot, right? You put a tea kettle on the stove, you put water in the tea kettle, and what happens is that when it gets really hot, it whistles. So the tea kettle is whistling, thus it must be really hot. Well, what's happening is the liquid nitrogen for us is really cold. But because nitrogen boils at a very low temperature, to the nitrogen in the tea kettle, the surroundings are really hot and the nitrogen is boiling away. So just to show you what it looks like. We have a thermometer here, and we're going to take a look at what our temperatures are. So here we are. This is sort of the range where we live. 0 degrees Fahrenheit is really cold. Here's body temperature, 98.6. Up at the top, water boils. But we pretty much live here. But we have to come all the way down to here for liquid nitrogen. Liquid nitrogen, minus 320 degrees Fahrenheit, 77 Kelvin. That's 77 degrees Celsius above absolute zero. Liquid nitrogen is closer to absolute zero by far than it is to where we live. So this is 2/3 to 3/4 of the way to absolute zero. This is really cold stuff. So the question then is, what would happen if Perry put his finger in the liquid nitrogen? Now, Perry, unfortunately,
I'm not volunteering.
is not volunteering. However, we have flowers that have volunteered to do this. So Perry, if you want to take 2 of the flowers.
All right. Let's get them nice and cold now.
You can hear the boiling. The flowers are really hot. They're 300 degrees hotter than the boiling point of liquid nitrogen, making the nitrogen boil. When the boiling sound stops, then we know the flowers are at liquid nitrogen temperature.
Almost there. I'll give 1 to you.
Looks fine, doesn't it?
All right. Brush it. There's
Yeah.
All right.
But it's very brittle. If I took a regular flour and I crushed it like that, it would be fine. This one, frozen. So the next thing we can look at is what happens if I put a match in liquid nitrogen. Now, there are a few different things that the match could do. The match could burn brighter. The match could not burn as much. Nope, just leave it.
That's
I'm
good.
All right. Match could just stay the same. It could go out or it could explode. So which of those do you think the match is going to do? Here's my match. Just in case it explodes, I'll be down here. And you notice that the match went out. Why did it do that? Well, I didn't put it in the liquid nitrogen. The level of the liquid nitrogen is down around here. The match only went into about here. I can put my hand in here. No problem. It's like reaching into the oven to get cookies. Air is a very poor conductor of heat, so you can reach in and put your hand in the oven. As long as you don't touch any of the metal bits, you're fine. So let's take a look. The way we'll take a look now is I'm going to put some more liquid nitrogen in this cup. And then, Terry, while I'm doing this, if you would refill the dewar, please. And you can see that liquid nitrogen is boiling away. We've got a couple carnation petals in there. Here's another match. What I can do, this cup is full mostly of cold nitrogen. So if I pour it out onto the match goes out. So the match went out not because it was so cold, but because there was no air. And all the liquid nitrogen that was in the dewar that was boiling furiously was turning into cold gaseous nitrogen. And so the dewar is full of liquid nitrogen in the bottom. The top 3/4 was gaseous nitrogen. Flame needs oxygen. There was no oxygen. Same thing here. Liquid nitrogen in the bottom, gaseous nitrogen in the top, and I can pour it out. And that fog, the water vapor, shows us where the liquid nitrogen, or where the gaseous nitrogen is flowing. Now, one of the things we're going to want to look at is how different materials behave when they're cold. So I've got a racquetball. I've got a ping pong ball, and I've got a super ball. The next thing I have is I have a pewter cup here that I can hold it by the handle, and it's pewter, so it's a beautiful bell, right? Clunk, clunk, clunk. Okay, it's not a very beautiful bell. Maybe we can change that. So we'll put the pewter cup in the liquid nitrogen, and we're putting them in now to give them time to get cold. And again, liquid nitrogen evaporates really quickly, and all this fog here is the same fog you see in a cold day when your breath condenses.
All right. So we're going to give those objects a couple of minutes to cool off, start getting down to that cold temperature. In the meantime, let's bring back to our concepts of what's happening to pressure. Like when I say I've got a balloon. What happens to the balloon when I introduce it to the liquid nitrogen? What's going to happen? All right. Go ahead and bring it in. That air inside the balloon is getting cold. Oop. Cold air reduces the pressure. As soon as I pull it up, you can see it start to expand again. It's starting to come back to room temperature. Come on.
Okay, now put it in and leave it in.
Now we'll just...
Let's see what happens when it gets really cold. So you notice that as it gets colder, the air's volume's decreasing, the pressure's decreasing, it's getting smaller and smaller. Just let go. Just let go. Yep, just let it go.
Oops, sorry.
And the other thing is that, well, this is liquid nitrogen. The air in the balloon is oxygen and nitrogen. The oxygen is liquefying. The nitrogen is also liquefying. So, in fact, there's just a puddle of liquid air at the bottom of this balloon. But as it warms up, it becomes gaseous again, and it expands, and looks like it's doing okay. And in fact, if I heat it up with my hand, then it's going to expand even faster. You notice I'm heating it up with my gloved hand. Need to be careful here. Now, one of the things that happens is that, we put the balloon in the liquid nitrogen, it got really small, it got really cold, we warmed it up again, it's fine. We put the flour in the liquid nitrogen, and you can see that this flour was never in liquid nitrogen. This flour, which was frozen and warmed up again, it's warm now, doesn't shatter, but it's looking pretty darn sad. So if you had any thoughts of immortality, having yourself frozen in liquid nitrogen in order to be revived later, you'll come back like this really sad flower if you're not very careful. The reason for that is the cells in the flower, the cells in our body, have cell membranes and cell walls. When it freezes, it makes ice crystals, breaks the cell walls, breaks the cell membranes, turns the cells into mush, and no, they're probably not going to be able to revive you 100 years from now to cure whatever ailed you. Okay, so.
Going back to, we saw when we chilled the balloon, how it collapsed. Let's see what happens when we let that liquid nitrogen, thank you, when we let the liquid nitrogen sit in a closed container. Oop, don't want the ping pong ball. Keep getting it.
More than that.
Yeah, I mean, there we go. So, not even sealing it. You can see how it's constantly expanding outwards. That gas, as it's evaporating, is pushing out. So now we're going to seal it. So what happened? I trapped the gas. The gas inside is constantly evaporating. The pressure is building up inside the soda bottle until finally the seal breaks and it pops.
And so the other point to make is what makes an explosion is not the expanding gases, but the fact that they're confined. So when I just put liquid nitrogen in this cup, it boiled away, no problem. But if I put liquid nitrogen in this bottle and seal it, then the pressure is going to build up until it releases somehow, and depending on how tightly it's sealed, that can be a really big boom. Liquid nitrogen, yeah, we'll just dump some out. So what we have then is we have a few balls, and okay, we've got the racquetball, feel that later. Put that back. Ping pong ball. What happens to a really cold ping pong ball? Does it bounce higher? Does it bounce lower? Does it shatter? Well, it's a ping pong ball. It's basically just like it was before. No problem. Let's take a look at ball in here, a super ball in here somewhere. Okay, super ball. Is it going to bounce higher, bounce lower, or shatter? Well, super ball is not bouncing. So the super ball became a lot less elastic. Last, let's take a look at the racquetball. So, racquetball, going to bounce higher, lower. There, it just bounces, doesn't bounce, but what will happen is if it hits something hard enough, it shatters. Carpet that I hit it on the first time wasn't. And then, last of all, we've got the pewter cup, which, remember, it gave off such a lovely thud last time. Now that it's been really cold, it's a nice bell. So with that, I thank you very much. Thank you for joining us. Thank you.
Thank you so much, Larry. With me today are three engineers, one from each of the organizations that helped collaborate to put this event on each year. Joining me today from NASA is Jesse Quinlan. From Newport News Shipbuilding is Tim Herman. And from Jefferson Lab is Jonathan Creel. Thank you, everyone, for joining me today. Before we hear from our panel, I want to remind everybody that's viewing that these engineers are available to answer questions you may have. Just put your questions in the chat during this panel discussion. All right, let's hear from our engineers now. Tell us a little bit about yourself and what you do at your job. Jesse, let's hear from you first.
Thank you, and good morning, everybody. So I'm Jesse Quinlan. I am an aerospace engineer at NASA Langley Research Center in Hampton, Virginia. I'm in the Aeronautic Systems Analysis branch, where I do really a whole slew of things related to conceptual aircraft design. And I serve as a team lead for a team called the Systems Analysis and Integration Team for the Advanced Air Transport Technology Project, or the AATT project. And the AATT project is a NASA aeronautics venture that's really tasked with developing advanced technologies and maturing technologies that might enable the next generation of commercial subsonic transport aircraft. So if you watch the airplanes take off and land out of Patrick Henry, I'm sure you've probably seen some Boeing 737s and some Embraer regional jets. These are the types of airplanes that we work on, and we do so from the perspective of conceptual aircraft design and systems analysis. And at the end of the day, what we're tasked with doing is developing aircraft models, performance models, performing trade studies and technology assessments and performance benefit assessments, all with the objective to better inform NASA management when they have to make a decision relating to our research portfolio or test plans or project plans, and ultimately help the United States aviation industry pursue really advanced aircraft configurations that may be too risky, may be outside the scope of day-to-day business, but that offer a lot of potential to achieve really long-term visions relating to sustainable aviation and the reduction of emissions and the mitigation of adverse climate effects on account of aviation. So we have a lot of fun with a lot of really cool aircraft concepts and configurations, one of which is behind me here. Hopefully you can see that. That's the transonic truss-braced wing. And that's a really neat aircraft that is able to generate some additional aerodynamic efficiency through this really long, slender wing that you see that's really enabled by that truss. And maybe we'll get a chance to talk more about that later this morning. Thanks.
Thank you, Jesse. It just sounds like you have way too much fun at your job.
Guilty as charged.
Thank you. Okay, Tim, let's hear from you next.
Got to figure out what the unmute button is. So kind of my daily job is making sure that our network is protected. You may have heard in the news about the Russia, U.S., all this stuff that's going on with Ukraine. Russia said, if you're gonna, we won't get into all of that, but it basically, they said you might have some offensive cyber attacks that hits the United States or something like that. We don't deal with all the United States. We deal with Newport News shipbuilding, and the reason is because of what we build there. We are the backbone of the United States Navy, building these aircraft carriers, nuclear-powered aircraft carriers, and there is a lot of engineering that goes into that. So even if you take anything away from this today, you don't have to be a cyber engineer. You can, like anything, you can go over there and find something to do. If nuclear is your thing or whatever. And it's funny because I spent 21 years in the Navy. I was on an aircraft carrier twice, but I don't know. They're really too big. They're like floating cities. So I always stayed below decks, safer that way. But it's I don't know how to say it. It's a lot of fun. It's a puzzle every single day. There's no two alerts that we get. I'm gesturing at my screen like you guys can see it. There's no two alerts that we get that are almost the same. Everything is a different person. You have to take it into account. Well, I don't know, just everything. Everything is a brand new slate. So if you like solving puzzles and trying to get to the bottom of things and why this computer was talking to this one, and protecting our network, keeping our sensitive and proprietary information out of enemy hands, I guess you could say. That's kind of what we do.
And that's important, Tim, because I know that this cybersecurity, everything is digital these days, and there's so much information that crosses the internet. Yeah, that's an important thing that you're involved in. Thank you. All right, Jonathan, let's hear from you next.
All right. So I'm Jonathan Creel. I'm head of the Cryogenics Engineering and Operations Department here at Thomas Jefferson National Accelerator Facility. So JLab is the home to a world-class electron beam accelerator that's used to research the basic fundamental building blocks of the atomic world. Our department contains about 50 engineers, designers, welders, and pipe fitters, and we design, build, and operate very large cryogenic helium plants across the country. 5 of the plants are located here at Jefferson Lab, and they're used to cool down various parts of the accelerator down to temperatures like 2.08 Kelvin. These cryogens are used to cool various parts of the accelerator, and it allows them to perform the functions that the physicists need them to perform. And it includes cooling down things like the cryomodules, which are the pieces of equipment that accelerate the beam, large superconducting magnets, which are used around the site for bending the beam or for filtering out particles from the beam as the beam goes through the center of these large solenoids. And it's also used to cool down cryogenic beam targets, where they shoot the beam into liquid helium or liquid hydrogen targets to look at what comes out of that. 2 of our machines here are called the central helium liquefiers. They provide cryogens to the LINAC, and they are the largest 2 Kelvin machines in the world. And each one of them uses about 5 megawatts of electrical power, just to kind of give you a scale. That's about the power. Them combined together is about the power it takes to run 10,000 homes. So these are really large refrigeration units. So I personally have been involved in designing and building the cryogenic plants here at Jefferson Lab. I've also worked on cryogenic plants at Michigan State University's rare isotope beam facility, Oak Ridge National Lab's spallation neutron source, the Johnson Space Center, where they have a huge vacuum chamber that we helped them replace their existing cryogenic system there so that they could take the James Webb Telescope and put it in there and run some tests on it, where they basically simulate it being in the space environment where it's going, where it is right now, in fact. And I also working on right now for Stanford University. They have the LCLS-2, which is a very powerful X-ray source that's going to be coming online in a couple of years. In each of these efforts, our group not only tries to meet the needs of the customers as to how much they need cooling, how cold do they need it, but in each iteration of the work we're doing, we as engineers are trying to make the cryogenic plants more efficient. So they use less electricity, they use less liquid nitrogen, they use less helium. Those are all valuable resources that cost quite a bit of money in order to use those. And we try in each iteration to reduce those as much as possible. Thank you.
Thanks, Jonathan. Sounds like you have a really cool job. Sorry about that. I had to say it. All right. Okay, so now I've got some questions for each of you. And let's see, this first one is for Jesse. Jesse, if I was a high school student and wanted to work as an engineer at NASA, what are some of the things I would need to do right now?
Thanks. That's a great question. And I'll first start by saying that we work with high school students all the time, actually. We have internship programs that high schoolers can apply to. We have internship programs that college students can apply to, graduate students can apply to, and I'll talk a little bit more about that in a second. But if I go even maybe a level higher than that, and if I imagine I'm a high schooler and I'm interested in working at NASA, what are the things that I probably should be doing? The first is, if you haven't developed a strong affinity for reading, I encourage you to do so. Read as much as you can, develop a genuine curiosity, right? So one of the things that we look for in engineers is a real genuine curiosity, because one of the most stubborn things I've found in life is an engineer who's trying to solve a problem. He or she does not let it go until it's solved. And that usually stems from a real genuine curiosity in the technical matter or the subject matter to some degree. Also, we don't just hire engineers, right? So a lot of folks think NASA equals engineering. And that is true to a large extent, except that there are literally thousands of people that work at NASA that are not engineers. So we think of the engineers and the scientists, but we also have to think about all of the lawyers, right? We deal with patent law all the time. We deal with communication. So we have lots of communication specialists. We have to be able to tell our story to the public. We have educators, right? Teachers and the like. We have educators to help explain our mission We have tons of management. We have financial analysts, business analysts, all these other potential career paths that still may put you at NASA, even if it's not engineering or science. The second point I'll make is, as a high schooler, if you can develop an affinity and an appreciation for math, that will come in handy and pay dividends time and time again throughout your life. And I say that even with there being a chance that you don't become an engineer, you really can't go wrong with math. I'd like to think of engineering and science, especially, as a house. And for anybody who has thought about how a house is built, or anybody who's crawled underneath their house, you know that every house is built on a foundation. And whether this is cinder block or concrete or posts that have been driven into the ground, you have to have a foundation to build a house on. And with a solid foundation, you can build the biggest, most grandiose house you can possibly imagine, but you can't do it until you have a foundation. And math is that foundation. And math is the foundation that we rely on at NASA to do our jobs, really across the board. The one other thing I'll say too is mentorship is really key. And I can think back to high school, I can think back to elementary school, I can think back to college, and even at NASA, mentorship is key. If you haven't already done so, seek out somebody that you would consider a mentor, somebody that you can bounce ideas off of and help you formulate a vector for your interest, a vector for your career and your studies. And that, again, will pay dividends. And then finally, internships. I mentioned it right here at the outset. We support all kinds of internships at NASA. And as a high schooler, we even support high school internships. So we just had a high schooler work with us this past summer. She did a fantastic job, and I'm happy to report that she's at UVA now, pursuing a mechanical and aerospace engineering degree, right? I can think back to lots of high school students that have worked with our branch and have had a chance to gain some familiarity with the type of technical work we do, gain some connections, which are really key to folks who are working in the field that they may want to follow up with later as they're maybe coming to the completion of a bachelor's degree or a college degree of some sort. And those are always great, really rewarding experiences for us too. We love working with high schoolers, right? We love working with college students. There's just so much fantastic energy and new ideas and creative thought. We can't get enough of it. So if you're interested, I encourage you to go to intern.nasa.gov. You can look at the process, you can put an application in, and I encourage you, even after high school, once you're at college, take a look at intern.nasa.gov. There's at any given time, usually tens, scores, maybe hundreds of internship postings across the country for NASA. So there's lots of opportunities there. And there's things that you can be doing along the way to help prepare yourself for when the time comes and the opportunity presents itself.
That's great advice, Jesse. And I know that when students, high school students especially, even undergraduate students, when they take an internship, it's really like a segue into a possible career at that center where they've interned. So yeah, internships are a big part of getting a head start on your career. That's very good advice. Okay, Jonathan, this question is for you. Is there anything you did or classes you took as a high school student that helped prepare you for your future?
Yeah, that's a great question. And everybody's past, varies as to how you get to where you get to. But I'm going to build a little bit on what Jesse had commented about a few minutes ago. And that is back in the early 80s when I was in high school, it's a long time ago. But I was unsure of exactly what I wanted to do, honestly, at that point in time. I loved math. I was good at math, good at science. I was really good with my hands. I enjoyed, taking things apart, working on stuff, electronics and mechanical. At that time, I was very lucky. A teacher there helped me get a job, a part-time job out at an Army helicopter testing branch out at Fort Eustis, Virginia. And I loved it. It was like everything gelled for me at that point. That job allowed me to work with very talented technicians and engineers. And I was able to actually get involved and do a lot of electronics work, a lot of mechanical work related to testing helicopter parts and pieces. And I stayed there through college, ultimately moving into their flight test branch. And I worked in their flight test branch for a number of years, performing flight test work, designing the packages and putting the things on the helicopters, taking them out and performing the actual test at various locations all over the country. And it it allowed me to perform flight tests on virtually all the helicopters in the Army's inventory, and including an air cushion vehicle that we tested one time. And it was an incredible time in my life, and it was very enjoyable. But I had always been interested in physics and accelerators. I had done a lot of reading back in high school, and it was just something that was kind of a passion for me. So I constantly kept my eye open for positions over at Jefferson Lab. And I finally saw one that looked like it was a good fit in the cryogenics group. And so I made that move over here. It's been 24 years now I've been here. And I've never been bored a day in my life. I will tell you, it's an incredible position here. It's allowed me to work with some of the most talented people in the world in cryogenics. And when we get to do the electrical parts, the motors and transformers, we get to design the compressor skids, we get to design oil removal systems, heat exchanger design, and all of these different things. And, that my education, getting with the right mentor, having them, help me decide the classes that I wanted to take in college, what college to go to. I had people like Jesse had said that were really advising me on how to make your life what you want. I look at education as a big tool bag, right? You're going out and you're getting education in different areas, and you're filling this tool bag up because you never know what's going to be that next thing in front of you. And it's really nice when you can reach in your tool bag and say, hey, I've done this, I've done that. And you can move right into areas that you never thought you would be able to move into. So, I've been personally very, very lucky in my life to have really great mentors and people to advise me, and just, education is important. Do your best in your classes and show people that you're really willing to push yourself and move to the next level constantly. Don't ever be satisfied with just sitting and saying, well, this is the same thing I do every day in my life. No, you got to push yourself. You got to work with the people around you to bring everybody forward as good as you can. Thank you.
That is excellent, Jonathan. And I'm so glad you talked about your teachers and speaking with your teachers. So your teachers right now, tap into them. A lot of them have connections around, the community, and can steer you into directions that you want to go that you might not even know are out there. All these opportunities. So your teachers, the principal at your school, your guidance counselors at your school, those are all great resources for students to tap into. So good. Thank you, Jonathan. Very good advice. So Tim, I have a question for you that's very similar to Jonathan's question. Was there a teacher or someone else in your youth who lit a spark in you, who gave you the motivation to go into engineering?
So, gosh, Jesse and Jonathan pretty much covered it all. I'm a little bit different. There was a lot of teachers that I respected along the way that I disappointed, I guess you would say. I was a miserable high school student, but it was, I don't know, it just intimidated me. I can't really describe it, but there's my physics teacher who taught my big brother. So when I got into the class and I would rather doodle or something else like that, he was pretty disappointed in me. I joined the Navy afterwards, and there's a lot of leadership, a lot of things to learn, mentors along the way. So I had a different path than these two guys, but I was a late bloomer, I guess you could say. So after 21 years in the Navy, then I decided I better go to college. I got to get smart, and and I think that my professor, I believe, taught ethical hacking. She was fantastic. She's worked with the DoD and everything else before. This was through University of Maryland. It was kind of like that little spark that that kind of lit. And I was like, oh, okay, this is cool. I can get into this. But touching back on high school, and I don't know, that when I grew up in the I'm going to date myself with John here, but graduating in the 90s, I just could not pay attention. Now they have, people kind of understand that a little bit more, but I was very smart and very intelligent. I just didn't want to do it. I would rather, I don't know, anything else rather than school. So I was scared actually to go to college. It was probably, even after 21 years in the Navy, it was probably one of the most scariest things that I've done. But it turned out I was actually a good student. I guess when you're paying for your own classes, rather than your parents, it's a different thing. But don't be afraid to go out and actually, don't do what I did. Well, you can, but don't let it intimidate you. And Jesse and John, math is so incredibly important. And I hated math. Math and I are like third cousins. We see each other at family reunions, but we don't really talk throughout the year. But I'm getting a lot better, and I wish I did have a foundation, a strong foundation in math, because now I got this little glitzy house, but my foundation kind of stinks. So, but that's I hope that answered your question. There was a lot of teachers that were kind of disappointed in me, rather than along the way. And then it was just that sorry, someone opened up the door behind me. But it was just you got to make sure that you do something fun, do something that you love to do, because you really, just like John said, he loves what he does, Jesse, and you don't really work a day in your life when you're doing something that you love.
Thank you, Tim. And you know what? You're probably speaking to a lot of students. When you mentioned being a late bloomer, and it took you a while to finally find your little niche in life, but look at you. I mean, look at you now. So I appreciate that. And hopefully it has reached some students who are kind of hesitant about going to college or getting into anything in the STEM field. Thank you. Okay, let's see what we have here now. I have a question for Jonathan. Jonathan, tell us about your path leading to where you are now.
Well, I kind of mentioned that a little bit earlier, but I mean, I'll give you kind of the data points, and then I'll fill in a little bit. But basically, as I mentioned before, in high school, I got a job as a technician out at this helicopter research facility. And then through that, I was able to pay for college because like Tim said a little bit, you never know what obstacles are going to be thrown in your place. So when I first got right out of high school, just as I was entering my first semester in college, my father passed away. And so from that moment forward, it was, I pay for college myself or it didn't get done. And so having that part-time job and being able to work in that area, it also, at that point in time, back when college was more affordable, I was able to pay my way through college without any debt when I got done. Then I went on to become a flight test engineer, and I did that for a few years. Ultimately, I became the branch chief at that flight test engineering facility. And that's when I moved over to Jefferson Lab and was doing pure engineering work again for a number of years. And slowly I moved up to incrementally to more higher positions of authority. And right now, like I said, I'm the department head for cryogenics. And it's been a long process of just taking that next step, looking at what area you want to move in. Kind of like Tim said, you want to do things that are fun, because you're doing this for many hours of your day, many weeks of your life. And if you're doing something that you hate, it could be a very long life of just being miserable. And so, I was always looking to work with people that I enjoyed working with, doing things that I really enjoyed. And so I kind of stair-stepped through that in my career as I've moved along.
Have fun with what you're doing. Find what you love and pursue it. Very good advice. Very good. So, Jesse, this question is for you. Was there an event in your young life that inspired you to become an engineer?
Thanks. That's a good question. I think isolating a single event might be hard, but maybe I can talk a little bit more about my childhood and my background, and maybe point out a couple things along the way that really made a big difference. So I come from a really small town in Virginia, a town called Luray, Virginia. If you've ever heard of Luray or Luray Caverns, we're nestled in the Shenandoah Valley. And I was raised in Luray. We aren't typically known for our engineering and science prowess. It's more the Blue Ridge Mountains and the caverns and chicken farms and the like. And so I went to a pretty small high school. My graduating class was on the order of about 100 students, maybe a little bit less than that. I could count all of the AP course offerings on one hand, which when I got to college realized that, wow, that was really inadequate. I went to college with friends who had 30 plus AP classes in high school they could choose from, and it really blew my mind. So a young Jesse growing up in Luray, doing typical kid things, having fun and spending time on the river and being outdoors and going to school and at some point I started reading, right, and I started checking out books from the library, and I developed a real passion actually for reading everything I could get my hands on related to physics and science. And even before that, in elementary school, I think it was fifth grade, one of my teachers at the time pulled me aside and said she'd like to maybe keep me after school a couple days a week and teach me a little bit more advanced math. She felt that I wasn't being challenged enough in class. She could tell that I was getting bored and that my mind was going to other things. And so she said, why don't you stay a couple days after class each week and let's look at a little bit more advanced math and see if you're interested. And so I did, and it was really fun. We were talking about really cool math relative to the fifth grade curriculum. And in one of these conversations, she told me what engineering was. And it's funny to think back, because before that, I don't know that anybody ever told me what engineering was, right? I didn't realize engineering was a field. Engineering was a discipline. Engineering was something that I could pursue as a career. And it's really funny because even before that, a couple of years before that, every elementary school, probably at some point, students will take these sort of like aptitude tests, like what should you be, based on your interests when you grow up. And I swear I remember it like it was yesterday. I took this test and I got computer technician. And I remember thinking to myself, hey, that sounds pretty fun. I love taking stuff apart. If anybody remembers the show How It's Made, that was a childhood favorite of mine. I love anything I could do tinkering wise. It's like, computer technician might be fun. And I specifically remember looking through the list of all the options and not seeing engineering. And so the term didn't even register in my brain at that time. It wasn't until a couple of years later, my fifth grade teacher explained to me what engineering was. And she said, you should really think about this. If you want to do it, you will be able to do this. You've got the math aptitude, you can do this. And at that point, I realized that engineering was a discipline, it was a field, and that was actually really interesting to me. And so I started reading up on engineering. And all these things started crystallizing my just innate interest in anything that goes fast, right, from an early age, whether it was bicycles, motorcycles, cars, airplanes. I sort of have a need for speed, and something about airplanes and just the beauty of a wing. And once you understand how wings produce lift and how you can design for these various features and aspects, it's a very beautiful problem and very multidisciplinary and really scratches a lot of itches if you're really interested in aerodynamics and structures and propulsion and all these other areas. So anyway. Maybe that was a spark in some ways. I mean, just simply being told that engineering was a thing, engineering was a career, it put it on my radar and it allowed me to focus in on it. And what that really did was, when I think about engineering, science, math, anything else, you can't really solve a problem until you define the problem. And if you haven't defined the problem, then you're going to get solutions that are probably suboptimal. They're probably not ideal, but they're going to be a product of your assumptions that you've made on the possible. And if nobody comes along and tells you that you can dream bigger, then you may sort of, stay in your fish tank or stay within your, fenced backyard or whatever metaphor, I can pull out here. So somebody coming along and again, going back to the discussion on mentorship, this is where a mentor comes in. This is why a mentor or advisor is so important. Somebody needs to break open that shell and really tell you what's possible, because I know myself, coming from a real small town, I didn't have a natural tendency to think big. I was thinking, what could I do right in front of me? But dream big. There's literally no bounds. There's no constraints. I mean, with enough desire and passion, determination, you can literally do whatever you want to do in life, whether that's engineering or anything else. And I truly believe that. And so I think there were a couple sparks along the way that helped crystallize a lot of interest in my life and a lot of general, interest and passion, and set me on a vector that inevitably put me in engineering school. And then sure enough, I went to undergraduate and studied aerospace engineering and applied math. I loved it so much. I went to graduate school. I got a master's degree and a PhD in aerospace and mechanical engineering. Education has had such a big impact on me. I moonlight one day a week as an adjunct professor at the University of Virginia now, where I teach aircraft design. I take every opportunity I can to explain to the students that I was in their shoes, right? We were all in their shoes not that long ago. And sometimes all it takes is somebody simply telling them it's possible for them to really just rally around themselves and their own interest and their own expertise and their own ability and make that a success story. So, I think sparks like that are probably common to a lot of engineers and a lot of scientists and a lot of folks even outside the STEM fields. And so going back, that's how important a good mentor or a good advisor can be, I think, in your life.
And bless that fifth grade teacher that saw that you needed to be challenged and kept you after school a couple days a week. She was your little spark. And that's lovely. And shout out to teachers that do that and take interest in their students. Thank you for that, Jesse. Okay, this question is for Tim, and it's a two-part question, Tim. What do you enjoy most about being an engineer? And did you always know that you wanted to work with computers?
Wow. Get the hard one. Okay. So I'll tackle the last part first. Well, you kind of heard my background and how I didn't really want to listen in school. I was absorbing it, but I just didn't really. I don't know. I remember my very first computer class. I grew up in kind of like Jesse, a smaller town, Bloomington, Indiana. It's where IU is, Indiana University. My very first computer class involved an Apple, and I'm not even sure what it was. It was the green screen, and then it was 10 print, hello, and 20 go to 10. That was really my computer extent growing up in high school. I mean, computers were just beginning to be a new thing. And I don't know why, but I just kind of spoke their language. I've always just been, I don't know, it just kind of makes sense in my brain, which really served me well. Going into the Navy, I first started out as an undesignated airman, which means they give you, you're kind of used up those first 3 years until you figure out what you want to do. If there's a cruddy job, it's let Airman Herman do it. Okay. But there was a line in Black Hawk Down where the guy said, "Why aren't you out there?" And he said, "Well, I have something that keeps me out of combat. I can type." And honestly, that's kind of where it started. It I don't know. It's just always, the computers have always just made sense to me. They got me out of washing a lot of airplanes. I'll tell you that. I didn't have to. I worked up in operations instead of that. So, out on the flight deck and scrubbing airplanes and things like that. And that actually informed my decision where to go from there. And I became a cryptologic technical in the Navy. With that's all computers and electronic intelligence and things like that. So I don't really know. I'll say this. I put together my very first computer when I was working at an agency in Fort Meade, assigned there by the Navy. And I had an Army Sergeant First Class who said, hey, I want a computer. I was like, okay, order one. And he said, no, we don't have enough money. So find a computer. And I actually went around with a box to all these different departments and just getting pieces of computers that they didn't need anymore. And I took it back to my desk and I dumped it out, and I just kind of, this looks like it goes together kind of thing. I was successful. So that kind of helped set me up for my life now. But yeah, it was a lot of trial and error. And I'm sorry, what was the first part of the question? I totally forgot.
Let's see. What do you enjoy most about being an engineer?
Every day. Every day is a new day. There's no, like I said, there's no two incidents that you might get we get alerts on our for some kind of unauthorized activity, or somebody's doing something, or someone may be sending something classified out of our network, something like that. And we have to go in and see actually what these people, our users, are doing. And most of the time, it's nothing big. But there are occasional times, someone will send something out that they're not supposed to, or go to a website they're not supposed to, and we go in, we figure out who the person is, if their job and duties assigned fit that activity, I guess you could say. So it's almost kind of like being a detective, being we're not the internet police, but figuring out the mystery of what this person's intent was and what they were trying to achieve. And if it's something that's malicious, then or nefarious, I was waiting to use that word, then we take action after that. But it's just every day is a new day, and especially being in this field, you meet lots of people. And at Newport News, there's the people, honestly, I mean, doing what you love is one thing, but the people that you work with, that's an altogether different thing. One of my captains in the Navy actually said he was changing of command, where they passed the command over to another captain. And something struck me what he said. He said that the USS Typhoon, that was the ship I was on at the time, is just a hunk of metal. It's just, I mean, it's right behind us. It's, the USS Typhoon's soul is here, you guys. And honestly, that's the great part about working in a really good place with really good people. It just makes it more fun.
I agree. I totally agree. And going around and collecting parts to make your own computer, hey, that's like a big part of what engineering is taking things and making things work, designing things and making things work. So yeah, good answer. Okay, let's see. I have two more questions, and then I have a final question for all of you. Jonathan, what makes you come to work every day?
I had to find my mute button there. Was my mouse wasn't working there for a split second. I love what I do. I mean, you've already probably seen that from what you've gleaned from my previous answers, but I'm kind of like Jesse in the way that I love what I do. I enjoy the people that I work with immensely. We're like a family in our group, kind of thing. We help each other out. You know, we're constantly grabbing each other and running to go look at this or that, and we got to come up with a new design for something. I love the challenge. I enjoy coming to work at JLab because it's never the same thing day after day. I mean, we have new things happening all the time. We have to participate, like I said, in designs outside of Jefferson Lab at these other facilities. So you get to work with a lot of new people all the time. And, you know, I enjoy even the nighttime calls because part of our work is not only the engineering, the design and building of the new equipment, but we have to run it. We have to take care of it. It's like having a bunch of toddlers running around that need constant attention, you know, and the problems that come up are very interesting. You know, it's, you know, you have somebody call you in the middle of the night and they give you these symptoms and you puzzle out what's going on. And then, you know, you go take care of it. Those calls also come from the other facilities. So I still get phone calls from Oak Ridge, Tennessee, or the people at NASA Houston, different times when they run into really unusual problems. And that's the challenges are the things that I really enjoy. And working with a lot of these people are very fulfilling in my life. And I just love it. Thank you.
It's great to do what you love, I have to say. Jesse, this is the last one for you guys before I have a final question for all of you. When you were in grade school, what were your hobbies? What did you like to do as a young boy?
Well, let's see. Maybe at the top of that list would be getting in trouble. I kid. So as a young boy growing up in the I grew up on the Shenandoah River in Luray, Virginia, about 30 minutes outside of Luray. So I grew up in the mountains with no neighbors and quite a few dogs. And so basically anything that I could do outside or anything that I could do with my parents, you know, I was my dad's right-hand man every time he opened the hood on the car, which was very frequently. And so I developed a real affinity for really, I like to consider myself nowadays a DIY enthusiast. So anything that I could build or destroy and then rebuild or take apart and figure out how it worked was a hobby. I was an avid rock collector. I had 4 brothers. So you can imagine how hectic our household was out in the mountains with 5 boys running around. But really, you know, anything outside, and that included, you know, 4-wheeling and hiking and canoeing and kayaking. And we, you know, were really fortunate growing up in a beautiful part of Virginia. We had trails right outside our back door. We bordered the George Washington National Forest, and on one side and then on the other side was the Shenandoah River, essentially. So our summers were on the water and our winters were cooped up, usually under some snow, tending the wood stove, and that was a lot of fun. But really, when I think back, I can think back to lots of projects, lots of what I would call maybe DIY projects nowadays, but, you know, tinkering that really took a lot of my time and developed a lot of the, you know, the interest down the line here that ultimately steered me toward engineering. I was also an avid reader. Like I mentioned, I literally read, I think, every book related to physics I could find in our local public library. At the time, I actually was thinking about going into theoretical physics for college, and ultimately decided that was a little bit too abstract, that I was never going to get my hands on an airplane. If I went down that path, I was going to be stuck with theory and so anyway, I would say anything outdoors, a lot of 4-wheel and motorcycling, a lot of fights with my brothers, football, the typical things that I think a small town kid would probably cite on their list of hobbies.
It sounds wonderful. And your mother did a good job with 5 boys.
Yes.
So, Okay, I have a final question for all of you. And we will start with Tim. Let's see. If you could go back in time to when you were in high school, what advice would you give yourself?
What advice would I give? If I went back in time and told myself, I know that my high school self wouldn't believe the older me, but we'll go ahead and do this. Confidence. You can do anything. You really, really can if you put your mind to it. If you want something bad enough, you can do it. You have two hands. You can, if you have the will to go and push for what you really, really want. You have to find something that really, really matters. But you can do anything that you want. It's never too late. Don't give up. It's a lot of people in high school. I kind of gave up. I mean, I really, really loved chemistry and I loved physics, but just, I don't know, like I just didn't want to pay attention. And I actually gleaned a lot of stuff from the chemistry class. I set things on fire a lot. No, I'm just kidding. But don't ever stop. Don't ever stop learning one thing. And you can do it. With your willpower, you can accomplish whatever you want. Like I said, I was a miserable student, and I actually just thought I was dumb. I don't know how else to describe it. I just thought I just didn't, I didn't have it. And those lists of teachers that were disappointed, every single one of them said, you're smart. Like, what are you doing? What's wrong with you? And I just didn't know. I thought that I didn't really have a plan. I didn't really make anything of myself, or, I tried, I guess you could say, but I couldn't really find that footing. And going into the Navy was a blessing in disguise. I knew I wanted to get out of my small town in Indiana and see the world, and I did. And it really wasn't until, actually to kind of further answer a question from before, I had one of my captains from the USS Typhoon. He was great. We were repairing a radio, and I don't know how to repair a radio. I'm not an electrician. I'm not anything like that. But he came down and said, Tim, fix the radio. And I was like, sir, I don't know. I can't. There's no way. Because there is nothing that you can do to this radio that we can't undo. You just do it. And I kind of looked at it, and I actually started working around with it. And I mean, it was probably luck, but I got the equipment to start working again. But that was kind of a pivotal moment for me. That confidence, the someone that says you can do it, and I believe in you. And again, late bloomer. I guess that happened late in life, but yeah, don't ever stop. Don't ever stop aiming for what you want. Don't ever stop learning. Just make yourself better. I don't know what else to say. I think I've kind of ranted on there, but
that's great advice, though. It reminds me of the little engine that could. You can do it. You can do it. And if only your teachers could see you now, right?
Yeah, I think quite a few of them would be very surprised.
I'm sure they'd be pleasantly pleased. Yes. Okay, let's see. Jonathan, if you could go back in time, what would you advise yourself to do?
That's a tough question because, like I said, I personally feel like I've been very lucky. I was, in the right place at the right time with the right mentors and people leading me down a path that kind of got me where I am. I stand on their shoulders, to steal someone's phrase. I really do stand on their shoulders. And it's funny, even though, I'm at where I'm the age I am, I'm still in contact with a lot of the people that got me here. Some of them, unfortunately, have passed away now, but I always made a point to go back to them years. We would have lunch together with different people, and I would let them know how much their interaction meant to me and how much I owe them for getting me where I am. I mean, they really, it's exactly like Tim was saying. These are people that either contribute to your life and make it better, or they can take from you and make it worse. And I was very lucky from the high school on, where I was able to meet up with the right people and work my way towards something that was better than I am. And I try to do that, as Jesse was saying. I'm personally involved, as you know, Carol, in the education program here at Jefferson Lab. I go to schools, not since COVID, but I personally go to schools on my own time and try to tell people that this is what you can do with your life. You can become a technician, you can become a welder, you can become a pipe fitter, you can become a CAD designer, you can become an engineer, and you can contribute to these great things like these pictures behind me. You can contribute to building these things that are really monuments to engineering. And I'm always amazed every day that I get to come into work and get paid to do the things that I do. And, I would just go back in time and honestly, I would try to make myself share that more with other people that I knew at the time in high school. I had friends in high school that didn't have the success or didn't have the opportunities come to them like it did for me. And a lot of them, they just never went and tried to find mentors, to try to find people that they could to do that with. And so that's the one thing I would change, is to go back and try to bring more people along, with us. Thank you.
That's great advice. That's great advice, Jonathan. Encourage others. Yep, very good. Okay, Jesse, we will hear from you last. If you could go back in time to when you were in high school, what advice would you give yourself?
Thanks. It's a great question. And, as I was sitting here listening to the great responses from Tim and John here, I was trying to think of something that they didn't already say. So what I heard, and then I'm going to try to add on, even if just a little bit here, what I heard was perseverance, right? You don't stop, you don't give up, you've got to dream big. I heard the value of education and really embracing, education for the value it provides you, as well as your educators, and really showing appreciation for all their efforts along the way. I think there's an element of being lucky, right? So I think John might have mentioned the right time, the right place type dynamic, which inevitably is something to consider. Identifying really great mentors and advisors. I think showing gratitude to those who have helped over the years. I heard one thing that I want to dig into a little bit more, and that I especially think about when I think of the question you just posed, and my own experience coming through high school and even through university education, is it took a long time for me to really learn to appreciate the value that is teamwork. And I say this as somebody who, I love challenges. I love puzzles. I love really hard problems. I tend not to shy away. I tend to try to own the problem and just obsess over it until it's solved. And that's good and bad. There's two sides to every coin. And so for a long time in my life, I was, very individual in how I approached technical work and technical problems and my education and my schooling. And, I was just fortunate along the way to have these really, really great interactions with educators and colleagues and team members and stuff. It wasn't until fairly late in life that I really learned to appreciate and value teamwork for teamwork's sake. And we heard this too in some of the responses to some of the other questions earlier. One of the things that I think Tim and John and myself would say is one of the best parts of our job today is our team. It's not us, right? It's our team. It's everybody that surrounds us. And I think as an engineer, especially going back and thinking to myself in high school, if somebody would have told me, hey, I know that you got your sights set on the edges of the universe, and you'll get there eventually, but you gotta develop some appreciation for team dynamics and teamwork, and leverage those around you and help them in the same way that they help you, and really learn that you're part of a team here, whether it's the human race or whether it's your systems analysis team at NASA Langley. You're part of a team whether you like to believe it or not, and you have to embrace some of the dynamics and some of the opportunities and some of the value that offers. So that might be the one piece of advice that I would give myself in high school, in addition to all of the list of great things that we've heard from the others already. That might be one additional thing that I would tell myself.
Yeah, and I'd just add one quick thing too. I mean, the value of teamwork is immense. And like I said, I've been lucky because in our group here, we have all of the flavors of all of the different technical capabilities that are needed to design and build these plants that are behind me. And one of the big things that I've learned over my career is that by getting the people that are fabricating things together with the people that are designing things, we learn a huge amount, because as engineers, we're constantly thinking of these great things that we're designing, and we're not thinking about the guy on the floor that's trying to build it. And they'll come to you sometimes and go, "This is great, can't build it. There's no possible way for me to do this." And so then you get to, work together to come up with a solution that works. And those are the really fun times.
Hey, you guys, this has been awesome. And I know that our viewers they must have enjoyed this, because I certainly know I have enjoyed this. Thank you so much for taking time out of your day to speak to these students. And I appreciate it. I appreciate it a lot. Thank you so much.
Thank you.
Thank you for the opportunity.
Joining us now is the Peninsula Engineers Council Doug Ensor Award winner, Dr. Robin Hunt. The Doug Ensor candidates must be less than 35 years of age and have less than 15 years of professional experience to be considered for this award. Welcome, Dr. Hunt. Thank you so much for joining us today.
Thank you, and hi everyone. Welcome to Engineering Career Day. Once again, I'm Robin Hunt, and I'm a research engineer at NASA Langley. I've been at NASA for about 4 years now, and it's been extremely rewarding. As an engineer here, I work on high-speed engine design. Specifically, I research ramjet and scramjet type engines that can fly at supersonic or hypersonic speeds, so faster than the speed of sound. And these are engines that could propel the future generation of commercial airplanes and let us fly across the ocean in an hour. And they're also an option for taking us to space as a reusable first stage in a 2-stage to orbit launch. So most of my work here at NASA is done in wind tunnels. And we basically design and build an engine, and then we put it in the wind tunnel to test how it performs and explore the airflow and the combustion process. And it's this hands-on work in a team environment that I really enjoy. But when I was in high school, I didn't really know what I wanted my career to look like. I knew that I liked science, so I explored a lot of different STEM classes. And I kept exploring during my first few years of college by taking everything from physics to biology to engineering. And I also learned a lot about different careers through summer internships, which are a great opportunity to get real-world experience and really develop an interest in a field. So it's great to see that all of you are exploring engineering by participating in this career day. And I encourage you to keep exploring so that you can find something that you're truly passionate about. So good luck today in the Cyber Challenge, and have fun.
Thank you for your inspiring words, Dr. Hunt. And congratulations on winning that amazing award. Good job.
Thank you.
Welcome to the Engineering Career Day Cyber Challenge. Here, you'll get to experience a competition similar to those used by cybersecurity professionals to train and challenge themselves. The challenges you will solve are derived from the fields of cybersecurity, computer science, mathematics, and beyond. While this is a competition, the problems should be fun to solve and give you a taste of what computer security and computer science are like. You are about to participate in a capture the flag style event. These types of events are used by the Department of Energy and an industry to train and challenge cybersecurity professionals. For your challenge, we will be using the Moth Capture the Flag framework. Moth was originally developed at Los Alamos National Laboratory as a training tool and has been used within the Department of Energy and other private companies for cybersecurity training events. Today, we are using it to host a set of challenges to introduce you to the field of cybersecurity. So, let's get started. First, log into your device. From there, open a web browser and navigate to the URL you have been provided with, like so. Before beginning, each team must decide on a team name. Take care to ensure that each team member uses the same team name. Each team has its own unique team ID, which you should have received from your teacher or the event organizers. This team ID is like your team's password and should be kept secret from other participants. When ready, enter your team ID and team name and click Sign In to register your team and enter the competition as shown. The competition's many challenges are broken up into various categories. The categories and problems are shown on the website's home page. The difficulty of a challenge increases as its point value increases within the same category. Therefore, two challenges with the same point value in different categories may not have similar difficulties. When attempting to solve a challenge, it is important to carefully read the problem, as some answers may require a special format. Such formats may include separating multiple values with commas or submitting the answer in lowercase. Some of the challenges in this competition can be quite difficult, but it is important that you do not give up. This challenge is scored, and you can view all of the team's scores on the scoreboard page. All challenge categories are weighted equally. So, the numerical value of a problem only reflects its weight within its own category. A problem with a value of 10 in one category may be equal in overall value to a problem with a value of 1,000 in another category. You can strategize and prioritize problems accordingly. There is a time limit on this event, and the winners are the teams with the top scores at the end of the time limit. Good luck and have fun.
This concludes the morning session of Engineering Career Day 2022. I hope you're inspired to learn more about the many different types of engineering out there. Hopefully, in a few years, you'll end up at Jefferson Lab as an engineer. Good luck with the cyber challenge this afternoon. Goodbye.